whole bunch of videos to do with exercise 6F, and those exercises are a further study of cubics. So in Wednesday's lesson, I went through this kind of thing where we had a cubic, which instead of having turning points, traditional maxima and minima kind of things, instead we had this idea of an inflection point, a point where the graph stops being concave down and starts being concave up, or if it's reflected, it'd be the other way around, stops being concave up and starts being concave down. So an inflection point denotes the change in concavity. Okay, so there we go. That's an X cube graph. But there are other graphs as well. Unlike a quadratic basically is smiley or frowny and that's it. But a cubic can change. Effectively, this middle area can get stretched out. So you can see here I've got two examples of cubics that are written in factor form. So I'll turn off the inflection one. Probably turn that off as well. Probably doesn't make sense in the context of this. And I'll turn on this. This is one example. There's so many examples. This is just one example. Now, in terms of how to graph it, they're in the videos that I created yesterday. And if you've watched them, then you'll be okay with that. But basically, when you've got multiple factors of a cubic, then just like in a quadratic, each of those factors becomes a possible solution using the null factor law for x. So they end up being zeros, remembering that zeros is just a fancy term for an x-intercept, and an x-intercept simply means what is the value of x when y equals 0. So for this one here, you can see that I've got one x-intercept at 0 because that's, I should do it with my cursor so that if it's on the video, you can sort of see what I'm talking about. This intercept here is 0, and we've got a factor over here, which is just x. Null factor law says one of the solutions is x equals 0. We've got another x-intercept here, which is at 1, which is the solution for when x minus 1 equals 0. And we've got another x-intercept, or 0, here at 3, which is the solution to x minus 3 equals 0. Therefore, x equals 3. So we end up with 3 x-intercepts, or 3 zeros, and then you have the curve going between those two lines. So you end up getting this roller coaster kind of function, like so. Is that okay with everyone? Kind of makes sense. The usual rule applies for working out the y-intercept. You don't have to expand the whole thing. I might just change this slide so we've got a y-intercept. Let's make this x plus 1 like so. I'll have to zoom out a little bit. So that's just to make it a little bit clearer, I'll make it x plus 3. That's a bit further away. So you've got x equals minus 3 as an x-intercept, x equals 1 as an x-intercept, and x equals 3. So minus 3, 1, and 3. Okay, so that's all right. We've got a y-intercept here of 0,9. And if you have a look at just the number part here, 3 times minus 1 is minus 3 times minus 3 is positive 9. So you don't have to expand the whole lot. Just multiply the whole number parts together, or the number parts together, effectively. Okay, and if there's a number out here as well, you'd have to multiply it by that as well. So if I go 0.5, just to squish my graph in a little bit, oopsies, you can see that it's now at 4.5, a half of 3 times minus 1 times minus 1. Anyway, I won't belabor it, but you get the idea, I hope. So that's basically how a cubic works. Now, the good news is these two things here, which are the turning points, they now have definite turning points. The turning points in this unit do not have to be calculated. There is, we all good? There is no precise method, calculation method for working out the turning point by looking at the x-intercepts. So with a quadratic, we just halve the distance, and that's exactly where the turning point would be, because in a quadratic, the parabola is symmetrical. But the turning point here is not halfway between -3 and 1. And the turning point here is not halfway between 1 and 3. It kind of is approximately, but it is not exactly. So when you're drawing the graphs, you can just estimate where you think the turning point would be, and that's fine. Okay. Now, for those who've done methods from Maths Extended last year, you'll know that you can work out the turning point using a branch of mathematics called calculus, right? Differential calculus, to be precise. So we will learn differential calculus later on in the year, and once you know that, then you'll be able to work out the turning points precisely. You can also work out points of inflection precisely as well, but that's for later in the year. So it's an absolute well-practiced thing that within the unit, you don't have to work out turning points at the stage. It'll say very clearly in the exam as well. Come.
Is there a symbol for approximately?
Yes. But you'll never have to label them in this unit. You won't even be asked to label it. But that's the symbol for approximately. In fact, if you look at your calculator, your GDC, I mean, there's an equal sign on your calculator. If you look above it, you'll see the approximate sign. So approximately equal to. Okay. Any questions about that? There is one trick. This has 3 unique factors. This next example here has just 2 unique. You know what? I might just change it a little bit. Just because it's slightly more interesting. I don't know what I was thinking when I just made it X. This has 2 unique factors, but I say unique because but it's actually got 3 factors because x minus 1 all squared is actually x minus 1 times x minus 1, right? So we call that a repeated factor. So a cubic has 3 factors. Doesn't always, but in this instance it does. It has 3 factors. It's just that the second factor is a repeated factor, okay? Or second and third is a repeated factor. And it looks a bit like this. I'm just going to zoom up on that repeated factor. You can see that 1 is the solution to x minus 1 equals 0. So it's dealing with that. And you can see rather than being just an x-intercept or a 0, it's also a turning point for that function. So if you see a repeated factor, then as in a factor to the power of 2, then know that it bounces at that point instead of cutting through. Okay, so a linear factor cuts through, a squared factor bounces. And if it's a cubic, i.e. x minus 1 to the power of 3, then it's going to be an inflection instead. Okay, linear cuts through, square bounces, cubic is an inflection. It's the wobble. It's the point where the concavity changes. All right, this is just a theory. Going through actual examples itself, there are videos that are on Google Classroom, so I'm not going to go through specific examples at this stage. Does anyone have any questions about the theory yet? What's that? How do you know whether the graph goes this way or the other way? Well, there's a couple of things that will allow you to determine that, particularly if you know what the y-intercept is. That'll pretty much join the dots to be able to draw it. But why do we know it goes, even without the y-intercept, why do we know it goes this way instead of going through here and then bouncing and going down that way as well? I'm glad you asked that question. It's a really important one. So this is the answer to it. There are things you can look at like reflections and stuff like that. But in one of the videos, I think it's the first one, I talk about this new critical piece of information called the dominant term. And I might just do this on the whiteboard. So sorry if you're looking back at this as a video later on. But the dominant term simply says from whatever form you've got it in, whether it's in just a usual cubic form or whether it's in factor form like this, the dominant term simply says, have a look at what's happening at the biggest power of x. So I've got x plus 3. I'm going to make this, I'm not going to draw the graph, but I'm going to make it a little bit different just to accentuate what I'm talking about here. X minus 1 and x minus 3. I'm not going to expand the whole lot, but I'm just going to multiply the x terms together, including a number that might be out the front. So I'm going to put a 3 out there as well. So what I'm saying is, what does the x cubed term look like? So I'll have 3 times 2, which is 6x, times x, which is 6x squared, times x, which is 6x cubed. Okay? 6x cubed. Now, if you remember from last lesson, what we talked about is the idea that what makes a cubic different from a quadratic and different from a power of 4 graph is that when you cube a negative number, the result is negative. Remember we talked about that? Okay, so that means that if my A value here, if this value here is positive, then when I look at values to the left, over this side, to the left of the graph, over this side, it means the function is going to be always negative. Yeah? So looking at the dominant term, looking at this, I can see, well, it's going to be negative, doesn't matter what's happening here so much, but like here, it's positive here. But ultimately, as I go further and further to the end, this x cubed term is going to be the thing that really dominates the equation. If I'm talking about a negative 1,000 x cubed, then it doesn't matter that you're squaring negative 1,000 as well. It's not going to be as powerful as the cube term. That's why we call it the dominant term. So if we look at the DT, the dominant term, that will pretty much tell us where the graph's going to start. So when I look at the left-hand side here where x is negative, this whole expression here is going to be negative. So I know it's going to start here. And the other good thing about cubics, and well, it's different in quadratics, but they have their own pattern, is that if it starts here, it's always going to end over here. Whether it's, I'll just do it here just for the video. If it starts here, it's always going to end here because of the way the cubics work. Okay? So whatever happens, we're going to end up here if we're starting here. Okay, so dominant term says, have a look at the highest power of x, in this case x cubed, and then say, what is its behavior? And if the behavior when x is negative is that this will be negative, then we know the graph's going to start here. And we know that it's going to end in diagonally opposite. Now, if I just change this slightly around, so note for video, what I've now got is 3 times 2x plus 3 times 1 minus x times x minus 3. Okay, if I look at this now and multiply it out, I'll have 3 times 2 is 6x. 6x times minus x is negative 6x. And negative 6x times x is negative 6x cubed. Okay? Now I've got negative 6x cubed. So if I take a negative value for x and cube it, I'm going to get a negative value. For example, negative 2 cubed is negative 8. But then if I multiply it by negative 6, then it's going to be positive again, right? So the dominant term, if this is the dominant term and the value of A effectively is negative, then it means I'm going to be starting in this quadrant, right? Because the resultant value for f of x is going to be positive all the way over to the left past this, what you can see on the graph screen. So if that's the case, then you're going to have it starting here and diagonally opposite, it's going to be ending here. And so you can go, oh, it's going to be like this or whatever. Okay, so the thing about the dominant term is that you can use the same logic for quadratics where you've got smiley and frowny based upon the value of A. You can also use it for powers of 4 graphs or anything, power of 7 graphs, whatever. Dominant terms are a really useful way of figuring out how your graph. And once you've got your graph sorted as to where it starts and where it finishes, then it's just a matter of just using your x-intercepts to graph out the rest of it. So just for the purpose of the video, I'll quickly just chuck these in. We can see that if I have 3 outside of 2x plus 3, x minus 1, x minus 3, we can see that it starts down here and ends up here, and the dominant term is 6x cubed. And if I just swap these around, the dominant term is now negative 6x cubed, and you can see it's starting up here and going to, and finishing down here. So a quick check of the dominant term confirms everything. Like I said, if you've got x-intercepts and y-intercept, then there's only one way of graphing it anyway. But this is what I've seen happen quite a bit, and it costs you tons of marks potentially. You've stuffed up working out the y-intercept. You've stuffed it up and you've made it positive instead of negative, or vice versa. So you've done that. You've not checked for dominant term, and so your graph is reflected. It's upside down. And so you lose marks for your graph being the shape of your graph, and you lose marks for your y-intercept. However, if you've ticked off on dominant term and you see that your dominant term does not agree with where you put your y-intercept, you can go, made a mistake there somewhere. Which one was it? And often it's the y-intercept, which you go back and check and then realize, shivers, that was supposed to be positive, and then you draw your graph properly. So it's one of those things where in an exam, you can't look at the back of the textbook and say, oh, I got it wrong. But the dominant term checking the y-intercept and the y-intercept checking the dominant term is a way of locking in good marks. That's a reason for doing it. Outside of an exam situation, if you've modeled something and you've got a cubic and you're trying to work it out and you're placing it there, then obviously using the dominant term will give you a sense that you've drawn the graph properly as well, outside of a textbook and outside of an exam. Okay, I'm going to stop this video and put it up on Google Classroom. But just to note then, the purpose of the rest of today's lesson for the next half hour or so is to complete the work from exercise 6F. There's just a few specific ones to do. I haven't gone through every single possible graph type here, but I have, I think, in the videos that I created for you yesterday. So it's a matter of going through each of the exercises, questions 1, 2, 3, 4, and 5, with question 5 being a graphics display calculator question. And it's a matter of having a go at them yourself. Get me to check your setting out would be a good idea, I think. But ultimately, you just want to be able to make sure that you're confident with graphing that kind of graph. And if you're not confident, go to the video. Or if you want to make sure that your setting out is as good and as efficient as it can be, maybe starting with your video and then trying them would be a good way of doing it as well. But it's up to you. And I'm talking too much, so I'm going to shut up. Any questions? Please, Richard, will you shut up and let us work? Yes, I will. That's a good question as well.